70. Well, so starting at age 60 or 70 or something like that. And what happens before that is essentially unknown, which I've shown here as being the black box. Now, this paper is a nice example of what might be in the black box and why it could be so important. What this group did was study the association of childhood poverty in the United States with brain development and academic achievement. Now, when we think about later life and say, for example, Alzheimer's disease, we're, of course, often thinking about hippocampal atrophy as a major component of Alzheimer's disease. But in this study, what they found is that in these children, they already had smaller frontal and temporal lobe volumes and smaller hippocampal volumes in childhood. And they found that the developmental brain differences explained as much as 20% of the academic deficits in low-income children. And then citing other research, they showed that these achievement deficits are associated with reduced occupational attainment. So showing how these early life cognitive functioning and what we might call cognitive reserve have impacts on later life functioning. So for us, this raised this kind of chicken-egg question. Do education and occupational complexity influence later cognitive outcomes, something that's purported to be the case in many studies of cognitive reserve, or is it reverse causation? In other words, do cognitive ability level and brain development influence educational and occupational attainment? So to address that question, we did that in this paper here published in 2018. And the data for this come from our Vietnam era twin study of aging, VETSA projects, which I'm the principal investigator along with the other two principal investigators, Michael Lyons and Carol Franz. And in VETSA, all of the subjects were in some branch of military service during the Vietnam era, sometime between 1965 and 1975. In our sample, nearly 80% report no combat exposure. And now there are just a bunch of middle and later age men living throughout the United States with little or no connection to the military. And if we look at health and lifestyle factors, they're very similar to average American men in their age range. So it's a community-based sample. In this study, we had 1,009 men, mean age of 62 at the outcome. And our measure of cognitive reserve is something called the Armed Forces Qualification Test, AFQT. And the AFQT is a test that they took when they were inducted into the military. And it's a nice measure of general cognitive ability, something that I'll refer to as GCA as a shorthand. As you can see, it's highly correlated with WAIS IQ, and it's very stable. We gave them the exact same test 42 years later at average age 62, and the correlation over 4+ decades is 0.73. Other variables in the analysis were education, including lifetime educational attainment, but also the amount of education they had at age 20 at the time they took the test. Because we were interested to see if that made a difference. And then we looked at other midlife factors that may affect cognition: occupational complexity, engagement in cognitively stimulating activities, physical activity, and health status. The outcome cognitive measures, there were 8 of them. The first is the repeat of this GCA measure at age 62, and then the others are part of an extensive neuropsychological battery where we had scores for the remaining 7 specific cognitive domains, these specific cognitive abilities. So let me walk you through this kind of complicated table here. So first of all, in the red box are the predictor variables that are in every model that we ran. In the blue box are additional predictors that were in some but not all of the models. And in the yellow box are 4 different models that we ran. And again, I'll walk you through this. Now, the numbers in the middle of the table are how many out of those 8 cognitive measures were predicted significantly by these predictor variables. So in model 1, we had lifetime education only in the model. And what we see is that there's some prediction based on occupational complexity and cognitive engagement, and 7 of the 8 cognitive measures were predicted by lifetime education. So consistent with what's seen in most studies like this of cognitive reserve. Now in model 2, we looked at lifetime education and also education at age 20. Now these are correlated as you would expect, but we did do some statistical checks to make sure that the multicollinearity was not a problem for the validity of the model. And what we see here is that, again, 7 out of the 8 measures are predicted by lifetime education. In model 3, we included lifetime education and age 20 GCA. Okay, I'm sorry, in model 2, just note that age 20 education didn't predict at all after accounting for the lifetime education. So back to model 3, where we have both lifetime education and age 20 GCA, now we see that only 4 of the 8 measures are predicted by lifetime education. So it still looks like some, but it's reduced, but all 8 are predicted by age 20 overall cognitive ability. Finally, in model 4, this was our attempt to add some precision to the modeling, and we took a subset of people, as 400-something subjects, who all had 12 years of education at the time they took the test, so that measure, we eliminate variance due to that measure that's held constant. And we looked at the prediction based on age 20 GCA and lifetime education. And what we see is that now lifetime education doesn't predict any of the cognitive outcomes after you account for age 20 GCA, but age 20 GCA predicts all of them. So what we're seeing here is that age 20 cognitive ability, so your cognitive reserve in young adulthood, is the main driver, not education. Now here, it looks like education may still be accounting for something. But remember, this isn't telling the whole story because we're just looking at how many significant outcomes there are, not the effect sizes. When we look at the effect sizes, here's what we see. So here we looked at the median % variance in specific cognitive abilities that were accounted for by lifetime. This is the 7 specific cognitive abilities by lifetime education, occupational complexity, and cognitive activities. And we see each of them accounts for well under 1% of the variance, whereas age 20 GCA accounts for over 10% of the variance. If you take the average of these 3, we find that age 20 GCA accounts for 16 times more variance than any of these. Then we looked at people who had lifetime education of 12 years, high school education, versus a 4-year university education. And we looked at what accounts for variance in GCA at age 62. Here you see age 20 GCA accounts for 40% of the variance, but education accounted for only 1.6% of the variance. Then we looked at change in GCA from age 20 to age 62. In the group that had just 12 years of education, there's a 0.002 standard deviation increase, mean increase in the GCA score. In the 4-year university group, there's a 0.084 standard deviation increase. So very little change from age 20 and not much difference between these 2 groups. It amounts to an equivalent of about a 1.23 IQ point gain for having a university education. In other words, it's less than 0.3 IQ points per year for those 4 years additional education. Now I'm showing some comparisons between our results and other studies, because in many other studies, the data are suggesting that increased education does increase your cognitive reserve. But ours doesn't seem to. So in this study of Clouston et al., they looked at 3 large British cohorts, and they found that having a 4-year university education gave people anywhere from a 6 to a 22-point IQ gain over just a 12-year education. And this is based on achievement test scores given in junior high school and early high school. But in VETSA, we see only a 0.4 IQ point gain. In the Lothian birth cohorts, the Scottish studies, where they had IQ measure at age 11, and then later gave it to different cohorts at either age 70 or 79, they averaged 1.18 IQ points advantage for each year of education. Whereas in VETSA, we only see a 0.33 IQ point advantage. And we also looked at change from prior to current cognitive reserve. And this is a comparison between the Lothian cohorts and VETSA. And I only compared those two because these two studies are the only ones that have the identical measure given in early life and in later life. And in the Lothian cohorts, we see there's a tremendous mean increase in the GCA score, from 1.12 to 1.51 standard deviations increase from age 11 to age 70 or 79. Whereas in VETSA, things remain very flat. There's barely any increase, 0.08 standard deviations from age 20 to age 62. So I'm going to come back in a minute to why we think we're seeing these differences and how that relates to early cognitive reserve. The last thing we did in this study was we went back to this analysis done by Errol Wuxema in our group, where we showed that neocortical surface area was a driver of general cognitive ability rather than cortical thickness. And the association between surface area and cognitive ability was almost entirely driven by shared genetic influences. So we looked at this in terms of education and the age 20 cognitive ability, age 20 cognitive reserve. What we saw is lifetime education was unrelated to either total cortical surface area or mean cortical thickness in our sample. But the age 20 GCA was significantly correlated with cortical surface area, but not with mean cortical thickness. So again, suggesting that it's the age 20 cognitive ability that's driving things rather than education. Or that another way of thinking about it is that it's the cognitive ability that's driving the educational attainment. So summing up here, we think the results are largely consistent with reverse causation, that it's not that occupational complexity, educational attainment, engagement in cognitive activities are causing the better later life cognitive function, which may then reduce risk for dementia, but rather it's the earlier cognitive ability which is driving those factors. So back to this question of why do these other studies find that education does increase IQ or GCA? What we think is going on is that the baseline of testing in these other studies average about 12 years. And what we think is happening is that education does provide an environment that promotes cognitive and brain development in childhood and adolescence when there's a lot of brain development going on, but that reaches an asymptote by young adulthood, whereas additional education doesn't provide, doesn't increase your cognitive reserve much more. And this makes sense in a way also if you think about it. If you just got this continuous increase in cognitive reserve and your cognitive ability with every year of education, well, everybody listening to this talk who are all PhDs or MDs we'd all be in the Einstein range for IQ, and that's not the case. So it seems clear that it does sort of reach an asymptote. There's also epidemiologic studies in Norway which support this idea, which is that they found when they increased the number of years of compulsory education in Norway, they saw this Flynn effect, this IQ increase, but it's leveled out and reached an asymptote. And so it fits with this explanation. And finally, I think our results suggest that there's a lot of limitations to education as a measure of cognitive reserve, even though this is probably the most commonly used measure of cognitive reserve. And a final example to drive home that point is this figure, which shows 475 people in the VETSA sample who all had exactly 12 years of lifetime education. So no variance in education. Education would be a useless measure in this group because there's no variability. But what we see in this figure is that there is a wide range of overall cognitive ability scores. So you lose a tremendous amount of information just looking at education. Okay, the next study I want to talk about is one that's not published yet. Hopefully it should be submitted in the next few weeks. Work done by Graham Eaglet, one of the postdocs in my lab. And it's about what happens between age 20 and age 60 in the black box. So as I mentioned earlier, in aging studies, we typically begin at age 60 or later, and that's our baseline in the study, but it's not really a true baseline because a lot's gone on before that. We just don't know about it. So in this study, we examined change in cognitive reserve from age 20 to age 56, average age 56, which was the first VETSA assessment. So I'm going to refer to the age 20 cognitive reserve as peak cognitive reserve because the 20s and 30s are generally what's considered to be where we reach the peak in general cognitive ability or IQ. And then the age 56 we refer to as the current cognitive reserve. So we asked the question, is a change in cognitive reserve from age 20 to 56 associated with performance in specific cognitive abilities at age 56? And is it associated with change in specific cognitive abilities from that point forward? So here we had 1,246 VETSA participants with 3 waves of study data. So the measures were our peak cognitive reserve measure, the age 20 cognitive ability measure. Specific cognitive abilities at age 56 and beyond, which are episodic memory, general fluency, semantic fluency, executive function, and working memory. And we also looked at some other measures that might be associated with cognitive performance in later life. An Alzheimer's polygenic risk score, a vascular risk index, and predicted brain age difference for people who had MRIs. Now, the predicted brain age difference is based on this software algorithm called B.R.A.I.N, which is taking free surfer variables for cortical thickness, cortical surface area, and segmentation, and subcortical measures. And they have a large sample with a very, very wide age range, and they're looking at what brains look like at different ages so that you can clarify someone's brain age. And then predicted brain age difference is basically looking at chronological age minus their predicted brain age. So for example, a negative value would mean that your brain age is estimated to be older than your chronological age, and so suggestive of accelerated brain aging. So to calculate the change in cognitive reserve, we used a regression approach. We calculated these residual scores. So if you're above this regression line, you would have a positive residual score, meaning that you would have better than expected current reserve given your peak age 20 cognitive reserve. If you're below the regression line, you would have a negative residual score, indicating that you have worse than expected current reserve given your age 20 peak reserve. So we refer to this as cognitive maintenance or maintenance of cognitive reserve over time, in this case from age 20 to age 56. So what we found is that maintenance of cognitive reserve was significantly associated with better performance on all specific cognitive abilities at age 56, as you would expect. Also, all specific cognitive abilities declined from age 56 to 68, again, what we would expect. But the rate of subsequent decline from that point on was not associated with maintenance of cognitive reserve from age 20 to age 56. So now we focused on the question, which is basically, is it how you got there or just where you're at currently? So in other words, and here, this is not a data-based figure, just theoretical figure. If people have the same level of cognitive reserve at age 56, but one group had been stable and at that level throughout life, the other group was at a higher level and declined substantially. Is their current functioning going to be determined by where they're at now or the difference in how they got to that point? So what we found is that after controlling for current cognitive reserve, maintenance of cognitive reserve was significantly but negatively associated with 4 of the 5 specific cognitive abilities. So to say this another way, given equivalent levels of current cognitive reserve at age 56, people who had higher peak cognitive reserve at age 20 perform better in specific cognitive domains at age 56, despite having the poorer cognitive maintenance. In other words, they had a greater relative decline over time. Their cognitive reserve is equivalent currently, but yet they're performing better in these specific cognitive abilities. So then we have to ask the question, is this just due to regression to the mean? And we think it's not, for a couple of reasons. One is that the residual score regression approach, we think, accounts for regression to the mean to a large extent because, for example, if someone has high cognitive reserve at age 20, based on the regression approach, they would be expected to have a lower score at age 56. But what we're looking at is their age 56 lower than that expected score? The second reason is that we found that poorer cognitive maintenance, greater decline from age 20 to 56, was associated with greater vascular risk and with accelerated brain aging based on the P.B.A.I.N. Was not associated with Alzheimer's polygenic risk. But the fact that it was associated with greater vascular risk and with accelerated brain aging suggests to us that this is a real effect and not just a statistical artifact of regression to the mean. So we're referring to this as paradoxical cognitive reserve because even though there's been a greater decline, in other words, poorer cognitive maintenance over time, the group with higher young adult cognitive reserve still seems to confer some benefit in midlife. Now, the other interesting point about this is that in a typical aging study, where we're beginning in mid or late life, this would be entirely missed because we don't know anything about what was going on at age 20. Okay, the last study that I'm going to be talking about is on impact of cognitive reserve and lifestyle on brain aging. This work was done by Carol Franz in our lab, one of the other vets at PIs. And again, this is looking at the P.B.A.I.N. measure. So what we did here was we had a measure of lifestyle where you get 1 point for not smoking, 1 point for not having excessive alcohol consumption, and 1 point for social engagement. So we can have favorable and unfavorable lifestyle behaviors. The lifestyle behaviors were measured on average at age 40, and then we're looking at the brain, the P.B.A.I.N. outcomes at average age 68. And the lifetime education in the group, the average is just under 14 years. Covariates were ethnicity, depressive symptoms, which may influence cognitive abilities, history of stroke, which included because smoking can increase risk for stroke, and ApoE genotype. So what we found is this lifestyle by cognitive reserve, young adult cognitive reserve interaction. Now, what I'm showing you here is focused on 3 groups of low, moderate, and high cognitive reserve, but the analyses were really based on continuous measures. We just divided these groups like this to make it easier to illustrate the interaction. And what we see is that the green line, those with favorable lifestyle, it doesn't matter whether you have low or high reserve, your brain looks pretty good in later life if you have a favorable lifestyle. But the group with unfavorable lifestyle, if you have low or moderate reserve, your brain is looking like you have more accelerated brain aging. But there's no difference for the high reserve group, suggesting that that high reserve is kind of protective against unfavorable lifestyle. So it's kind of 2 key messages in a way from this analysis. One is that up to now, you might be thinking that I'm suggesting that everything that happens in, up to age 20, that it's all over after that and that defines everything. But here we see that midlife lifestyle behaviors can have an impact on later life brain aging, which presumably is going to affect cognitive function and perhaps risk for dementia. The other thing is that it may be good news for people listening to this presentation, because I assume that everyone in this group is probably in the high reserve group. So our results kind of suggest that that means you can smoke and drink as much as you want, and you're still going to be okay in terms of brain aging. So the other thing about this is we wondered now, it got us thinking about this high versus low reserve. What is the meaning of high and low reserve? And are the findings generalizable? And I think, as I'm going to show you, this is an important issue that's kind of ignored in the literature. And the question is, do we need common metrics for high and low reserve? So here's 3 studies, all of which are well-done studies, one by Solden et al. From BioCard, where the average education is very high, 17 years. So if you're 2 standard deviations below the mean, your education is slightly more than high school education. So what's high and low reserve in this group is at the very high end of the scale. This is a study from VETSA, where we had a high reserve group with 14.9 years of education, and low reserve group with 12.9 years of education. So our low reserve group here is near 2 standard deviations below the mean in this study. Our mean IQ is about what 2 standard deviations below the mean in IQ is for this study. And in this study from the Columbia group, high education group was 9 to 12 years, so that low reserve in each of these other 2 studies would be solidly in the high reserve group in this study. And I think there's not enough attention paid to this across studies when people talk about the effects of high and low reserve, and what we're concluding about low reserve or high reserve in one study may not be applicable to another, given these kind of differences. So overall, we see that I'm concluding that education is probably a weak measure of cognitive reserve. Even when there's been a substantial prior depletion of cognitive reserve, higher prior cognitive reserve still appears to confer some protection or resilience against later adverse factors. Although we need to do more work to figure out what is going on there and why that is. Favorable lifestyle factors do seem to confer resilience against accelerated brain aging in people with low to moderate prior cognitive reserve. And I think we need to consider whether low versus high cognitive reserve, do we need to have some measures of absolute scores for high and low reserve, or if we're just talking about them in relative terms, we need to make sure to make some comparison with other people's definition of low and high reserve, because they may not be at all comparable. And finally, coming back to this question of, do educational and occupational complexity influence later cognitive outcomes, or do cognitive ability level and brain development influence educational and occupational attainment and engagement in cognitive intellectual activities? We think it's the reverse, that it's the latter, and it's reverse causation that's primarily what's going on. And without data on prior cognitive reserve levels, which is the case in most studies, reserve causation needs to be more seriously considered, and I think that it's rarely accounted for. So I'm running out of time. I'll just make one more point. Being a twin researcher, I wanted to talk about something genetic here and think about what's going on, why this reverse causation phenomenon might be happening. And this study is a study of 10,000 twin pairs, and they looked at the heritability of general cognitive ability from childhood to young adulthood. And they found that environmental influences tend to decrease over time. And it may make some sense to think about becoming more independent from the family environment as you get older. But the genetic influences on cognitive ability are increasing substantially. And why would that be? And we think it's due to something called active gene-environment correlation, which is when your genetic propensities lead you to seek out or select environments that promote the expression of those genes. So if you have if you have genes that predispose toward high cognitive reserve, those genes may predispose you to select out environments that support the expression of those genes, like going to the library, reading books, things like that. And that's where the reverse causation comes in. It's those things that are driving people to gain more educational attainment, engage more in cognitive activities, and things like that, not necessarily that those are causing the cognitive outcomes. And again, it's important to keep in mind that things like engaging in cognitive activities, for example, are not randomly assigned. So this is one explanation for how the reverse causation may work. So I will stop there. Thank you very much for your attention.
Thank you, Bill. This was a great lecture, very complex data. So please go ahead, everyone, and just unmute yourself and activate your camera if you'd like to ask a question. Just go ahead. Anyone?
Hi, this is Caitlin Cassetto. Sorry, my camera is not working. Thank you, Bill, for this really great lecture. I think it's a really compelling way to think about reserve and resilience in terms of sort of reaching a peak, and then maybe lifestyle can start to impact those factors. I was wondering I think you presented some compelling data about the reverse causality of these cognitively stimulating activities and how they may not necessarily be driving reserve in late life. But how do you interpret the data on cognitive training paradigms that show that engagement in these enriching cognitive activities might show some cognitive benefits even in late life?
Yeah, so a couple of things about that. I think it's an important point. So one is that for those to be meaningful, they have to be done in studies where people are randomly assigned to the training group or some other group, right? Otherwise, the reverse causation issue is problematic. But there are examples where it still shows benefit. And, so I think the reason is that it's not 100% reverse causation. But on the other hand, it's pretty clear that what you gain out of this kind of cognitive stimulation is kind of less and much harder to attain in later life than in young adulthood. And, I'm sure you know, those studies have been mixed in terms of either the strength of effects or transfer of training and that sort of thing. So it does seem that it's difficult to achieve a lot of benefit, and the benefit is relatively small compared to that kind of stimulation in younger adulthood. But that said, it's still, I think, well worth pursuing.
Yeah,
But
I think that's great. And maybe your data.
The groups aren't randomly assigned, then you can't conclude that it's causal.
Certainly. Yeah, I think it's a great cautionary note. And maybe your data suggests that we should really be targeting low reserve people who have room to grow.
Yeah, I think that there is evidence to suggest that the high reserve from early on seems to be more protective and affords people more resilience. And I think it's also suggesting that prevention of late life cognitive decline and reducing risk for dementia may begin in childhood and early adolescence when there's a lot of brain development going on, and that's what's the really key time for intervening.
Well, can I make a comment on this, which speaks a little bit to what Caitlin raised? So this reverse causation basically says that people live a life according to their early cognitive abilities. So they have an education, occupational complexity, cognitively stimulating lifestyle. However, it doesn't really tell you anything about the potential plasticity which may be there. So, people just behave the way, they are feel cognitively comfortable with, but if you would challenge them, what kind of plasticity you would expect, this is not really, pervaded by this correlation of reverse causation, right?
Yeah, that's we don't know that in this study. And, although our data is suggesting that, that again, this, I guess if you think about in early life, education is providing this stimulation, this enrichment that's increasing people's cognitive ability. And, as I point out, it seems to level out in early adulthood. Now, I don't think we know that well yet how far you can continue that enrichment, and whether you may not be increasing IQ, but by continually engaging in this kind of stimulation throughout life, it may be helping to maintain good cognitive reserve. Yeah. It's just, there aren't, we don't have the kind of controlled studies to really assess that.
Okay, thank you. Anybody else?
Hi, Bill. That was a really great talk. It was really interesting. I just wanted to ask, I suppose, a very general question, but given you've shown that education is maybe not a very strong proxy for a measure of reserve, would there be any maybe more suitable proxies that you might suggest to use for people who are restricted to using proxies to measure reserve?
Yeah, that's a good question. Because obviously most studies don't have these earlier measures. I think for English-speaking cohorts, measures like the NART or the RAT reading subtest, any of these reading recognition tests, which are real hold tests. And there was a study way back in the mid-'80s, comparing actually mild Alzheimer's patients and controls, and they found that the Alzheimer's cases were much lower in IQ, but were equivalent on the RAT reading, which is like the A-NAR.
Yeah.
So that's maybe the closest thing we can get to a pre-morbid IQ estimate that will have some more variability than, than education. It doesn't work in all languages. So for example, Harold Wolfsima, who was a former postdoc of mine, who's at the University of Helsinki now, has pointed out to me that you can't have a test like the NART in Finland because the NART relies on words that are not pronounced as they're written, whereas in Finnish, everything is pronounced as it's written, so you can't use the same kind of measure. So, a second best thing might be trying to use even something that's known to be a real strong hold kind of test that's, highly correlated with IQ, like vocabulary maybe, or something like that.
Thank you very much. Thank you.
Not a perfect solution.
No. Thank you.
So Bill, what do you think, to what extent is this age 20 general cognitive ability subject to early life enrichment variability? To what extent is it
I think it definitely is. It's, so in our sample, in the analyses I showed, one of the variables that we had as a predictor, as a covariate, was childhood socioeconomic status. But that didn't account for very much in our sample, but we do have some data showing that, that is a factor. And it's clear, from the study I showed about the children living well below the poverty line in the United States, which probably means they have poor nutrition, poor educational exposure. It seems very clear to me that is leading to not only poor academic achievement, but poor brain development. So I think that is a very big factor, and which brings me back to the point that more and more I'm thinking that the prevention of cognitive or reduction of cognitive decline in later life, that it's really these early childhood things that may be a big factor.
Mm-hmm.
In the United States, they had a program called Head Start, where children from low socioeconomic, economically deprived environments were put in these programs early, even pre-kindergarten, to get them more cognitive enrichment, and did show that it has beneficial effects.
Thank you.
So during the time of prime brain development is I think prime time for this kind of cognitive enrichment.
Well, it's great news that by now we can all get wasted. Yeah. Anybody else? Please come forward. Well, if there are no other questions, then thank you very much. Bill, that was a great talk. And yeah, thank you all for attending. Next time, Gail Chetela will present on meditation and cognitive reserve. Thank you very much.
All right, thanks very much for having me.
Sure. Bye-bye.
Bye, everyone.
Bye.